Hi everyone, welcome to the webinar, Determining Best and Worst Case Scenarios During Slope Stability Analysis. My name is Brent Corkum. I'm the Chief Technology Officer for Rocscience. I've been doing and coding slope stability analysis since 1985. I was part of the original team that started Slide, well, then it was called Slide 2, in the early 1990s. And I am the chief architect of both the Slide 2 and Slide 3 packages. Today I'm joined by Brigid Cami, who's been working at Rocscience for 6 years. She is currently the project manager for Slide 2, and she's worked on a number of features on Slide 2 and Slide 3, specifically spatial statistics in Slide 2, the probabilistic response surface feature in both Slide 2 and Slide 3, the multi-modal optimization searching that we've just released in Slide 2 and Slide 3, and she's done a lot of work on the modeling of support, and in particular pile models in Slide 2. I'm also joined by Terence Ma, who's been working at Rocscience for 1 year. He had 2 internships with me at Rocscience previous to that. He's worked on notable features such as the Slide 3 architecture, Slide 3 searching, such as the Metaheuristic Optimization, which we'll be talking about in this webinar. He's currently working on weak layer modeling, both in Slide 2 and Slide 3. He's also completed our work on design standards, Eurocodes and the British standard in both Slide 2 and Slide 3. And he's just finished also working on a cool new feature that we have in Slide 3 for modeling, for block modeling for mining applications. A little bit about Rocscience. We're situated in downtown Toronto near the streets of Queen and University. You'll see that's our building there in the center, and we also are in the building on your right, the historic Toronto Half House. You can see it's just been a house that's cut in half. And now we also have the building on the other side, which is not on this picture. So we have 3 buildings, and obviously we're a world leader in 2D and 3D geotechnical software for civil and mining. We've been in business now for about 25 years. We just had our 25th year anniversary. And we have about 10,000 customers, and we're around 60 employees now, of which over half have advanced degrees in engineering. Okay, a little bit of a timeline, a little stroll down memory lane here. That picture on the left side is the original Slide 2 development team. I'm the young guy on the right side. This is, of course, 20 years ago. And I'm joined there by Igor, Kavan, and Warren. And it was the 4 of us that really wrote the first Windows version of Slide, version 3.0. And of course, we're on version 9 now. So we started with development in DOS at the University of Toronto in the early 1990s. And even then, we were looking at cool new ways to change how slope stability software worked. In those days, we were looking at different methods of importing geometry. We had a number of customers that had DXF files, and the method at the time was quite antiquated. It was one of those left to right, top to bottom entry of the geometry. It was absolutely brutal to do anything in mining. And so we had to develop a whole new way of doing geometry. And at the same time, we were thinking about searching. And our early version of Slide is probably the first that I know of that had safety maps in them, where you could actually plot the distribution of factor of safety throughout the area of analysis. Rocscience was founded in 1996, and as I said, in 2000 we released the first version of Slide for Windows. And shortly thereafter, in 2003, we added something called Monte Carlo local optimization, which is based on a method developed by Greco in the mid-90s. But we quickly realized during this particular time that the searching in slope stability was quite antiquated, and you rarely got the correct surface when dealing with certain types of complicated problems. So we implemented the Monte Carlo optimization. We were probably the first commercial package to do that. And then at the same time, we started working on more global techniques because we quickly realized that local optimization was insufficient. And we started working on metaheuristic methods such as simulated annealing. And we'll talk a little bit more about the metaheuristic global optimization methods. And at the same time, we improved our circular searching as well, that we realized that the simple grid search lacked the power that we needed for hunting for the true circular surface. And then in 2015, we introduced the cuckoo search, which once again improved our ability to hunt for the true global minimum failure surface. And then in 2018, we added particle swarm, but really the most important one was we added something called surface altering local optimization. And that method, which is in both our 2D and 3D packages, will be talked about in this webinar. But its real advantage is that it takes over when the metaheuristic global optimization stops, and it better refines the surfaces in order to better estimate what the global minimum failure surface looks like. And it's particularly good in 3D. Then in 2020, we added multi-modal optimization, which allows us not only to concentrate on the global minimum, but on other possible minimums that you might have in your slope. Next. So the outline of today's webinar is that Brigid's going to talk about the first 2 points here, global optimization and local optimization. And then Terence is going to take over and talk about our new multimodal optimization, and he's going to talk about optimization in 3D, which is super cool and probably one of the most difficult optimization problems that I've ever worked on. Next. Okay, at this point, I'm going to hand it over to Brigid.
Thanks, Brent. Before we start, just 2 notes. If you have any questions, please type them into the questions box. We'll answer them both during the webinar and at the end. And before we dive into the different search methods, I'm going to start a poll that asks what search method you use. So feel free to answer that during the webinar. Okay, so it seems like it's predominantly grid search, followed by cuckoo search. Interesting. Okay, so as Brent mentioned, we'll talk about the global search methods. So we'll start from the original grid search and move on to the latest metaheuristic methods in slide 2 and slide 3. So before we do that, I just want to give the most basic definition of what slide 2 and slide 3 do. So say you have a big slope on the side of a highway here. You wouldn't want it to collapse and crush the cars. So you want to check if it's stable. And that's why you use slide 2 and slide 3. So in this case, for example, you would get the geometry of the slope and the material properties, plug it into slide 2 here, for example, hit compute, and slide 2 gives you this result. So it's saying that this specific surface is the one that's most likely to fail, and this is its factor of safety. As we know, the factor of safety is the ratio of resisting forces to driving forces, resisting forces being the ones that are holding the slope together, and the driving forces being the ones that are trying to pull it down, such as the weight. So in this case, the factor of safety is less than 1, meaning that in theory, this slope will fail. So the goal of this webinar is to answer the question, how did slide 2 determine that that specific surface is the most likely to fail? Brent talked about some of these methods, and how are they actually finding that exact surface? We can rephrase this question as, find the surface such that the factor of safety is minimized. So basically, this is an optimization problem. We all know about optimization from calculus. At its most basic form, it's just take the derivative and set it equal to 0. But for a problem like this, where there are so many components, for example, the geometry of the model, the material properties, different material models, and the slip surface itself has to be realistic, we have to be a little more creative than the derivative. So we'll start with grid search, the original searching method. The way grid search works is you define a grid with points evenly spaced inside of it, and each of these points is the center of a big circle. So for example, you pick this point and you draw a circle at this radius. Then you increase the increment of the radius, you draw another circle, and so on. You calculate the factor of safety of each of these circles, and then the one with the lowest factor of safety is the global minimum. So of course, there are some disadvantages to this. One disadvantage is that if you look on the grid here, all the green regions are the ones that had a high factor of safety. But this method, the grid search, still had to search in all of those regions, even though it knows the critical surface won't be found there. As well, there's the limitation to the circular surface. In a case like the image here, there's a weak layer running through the slope, and it's unlikely the surface would be circular. It would probably try to go through the weak layer. So that's where metaheuristics come in. So the metaheuristics, instead of spending a lot of time in these high areas, they're smart enough to know, after trying a few surfaces in this region, the critical surface won't be found here. So then they focus on the actual critical regions. And of course, they are not circular, so they're more flexible to any scenario. So what exactly are metaheuristic methods? Really, it's just a fancy word for a trial and error kind of process. But it's modeled after patterns found in nature, things like bees searching for honey, or the way birds fly in a swarm. Between slide 2 and slide 3, we have 3 metaheuristic methods: cuckoo search, particle swarm, and simulated annealing. So back to the question, how are these actually applied in slide 2? We'll look at particle swarm as an example, as it's quite straightforward to understand. So before we look at it in the slope stability sense, let's look at it in the traditional sense. So say you have some sort of crazy function like this, and you're trying to find the lowest value. So like the lowest factor of safety, in this case, it's just the lowest z value. So the way particle swarm works is first you just start with a bunch of guesses. So you start with a bunch of xy points throughout, and you get the z value there. And then the particles, the xy guesses, they can communicate with each other. And so for example, if there's a particle here that's starting to get low, it can tell the other ones, hey, this seems pretty good here. And then they all go in that direction. So now take this plot and pretend we're looking at it from the top. And that's this. So this blue dot here is where the negative seems to be. Sorry, the minimum seems to be. So these are our initial batch of guesses. And the way that the particles move from here is they follow 2 pulling forces. One is they go towards the lowest point. So that's this minus 5.2. So let's look at this particle, for example, how it's going to move in the next iteration. It goes in that direction. And the other force they're pulled by is its own personal best position. So this particle, its previous position was actually better. It had a lower value. So it's pulled by those 2 forces to go to the next iteration. And then this is repeated over and over again, like 500 times. So this is a little GIF of what this looks like. So again, pretend we're looking at the top. You start with a bunch of guesses and they all converge towards this minimum. Okay, so we have our slope, we apply particle swarm, and we get this specific surface. How exactly? To answer that, we can look at the search methods in slide 2. So here, for example, we've selected, first of all, non-circular search, and we've selected particle swarm search method. There are 3 inputs here. The number of particles, 50 particles, so that's the 50 guesses that you start with. The iterations, 500, so that's you repeat the particles moving 500 times. And the vertices, which is 8. That's the initial number of vertices on this polyline. So then how does this work in slide 2? Well, each one of those particles, which was an XY coordinate before, is now a slip surface. So instead of starting with 50 random points, you start with 50 random surfaces. And this is actually for this slope what the initial 50 guesses were. And you can see the legend. So the more yellow-red ones are lower. And even from the first 50 guesses, you can see that this yellowish region seems to be lower. So with each iteration, these surfaces will start to move in that direction. So that's global optimization. So say we run particle swarm or cuckoo search and we get our global minimum surface. Now we can make it even better using a local optimizer. So this is applied after the first global surface is found. And our famous local optimizer is called surface altering, which was actually developed at Rocscience. So what surface altering does is, like we said, you have your global minimum from cuckoo or particle swarm, then you add a bunch of extra vertices to it, and then you move those vertices little by little. So you start with the endpoints, then you oscillate the middle points until you get the factor of safety to be even lower. So to digest all of this information, we'll look at a demo, and we'll go through grid search, cuckoo search, particle swarm, and the impact of surface altering. So I have pulled my slide model here. So this is a slope with 3 different materials. Let's just take a quick look at the materials. This first one is shale, and the material model is a shear normal function. So that looks like this. There's normal and shear values. This green material is generalized anisotropic. So that means that a different material is assigned to different orientations depending on how the slip surface falls on it. So for example, soil mass and bedding, and they're also defined here. And then the orange material is anisotropic linear following the anisotropic surface. So what that means is that the anisotropic surface is this purple line, and that's going to be the weaker orientation in this material. So as you can see, I've defined a grid search to start, and now I'm going to add a couple of scenarios. And this first one is going to be cuckoo search, and this next one is going to be particle swarm. So I'll click on cuckoo, and I'll click on surfaces, surface options. So we switch from circular grid to non-circular. The default non-circular is cuckoo, and we also see that optimize surfaces is checked on. So that's our local optimizer. And if you click on settings, you can see that it's set to surface altering. And I'll click OK. And then I'll click on my particle swarm scenario and go surfaces, surface options, non-circular, and I'll select particle swarm. And I can expand the options here to see those 3 inputs that we were talking about earlier. And I'll click OK. And then we can compute to see what the results look like. So first it's doing the cuckoo search here. This is the global search. And then down here you can see that after that it does the surface altering. So again with particle swarm, the global search, and then surface altering down here. And I'll click interpret to view the results. So our first scenario is the grid search. You can see it's circular and the factor of safety is about 1.6. Cuckoo, the factor of safety drops to about 1.19. So that's already very significant. And you can also see that the surface now is not circular, and the one in this anisotropic linear material actually follows the anisotropic surface. So that's the weaker orientation. And I can also click on particle swarm, and it's a very similar surface, follows the weaker orientation, similar factor of safety. Now, one thing that's always good to do is to verify your results with different methods. So I'm going to verify my results with shear strength reduction. This is RS2, or 2D finite element software. And what I'm going to do is just drag that file we just made into here. And it's asking me which scenario I want to import. It doesn't really matter. I'll just pick Cuckoo. And then it's saying, do you want to turn on shear strength reduction? Yes. Automatically generates the mesh and everything else. And I click OK. And then if I click on material properties, I can see that everything is exactly as it was in slide. So I see my shale is shear normal, and I see my generalized anisotropic and my anisotropic linear, which is following this anisotropic surface. I don't have to change anything here. I just hit compute, but I did this ahead of time just to save some time. And we can see the maximum shear strain results. And you can see that the surface is very close to what we saw in slide. And actually, we can confirm that better. So I'm going to go here and I'm going to right click on the surface and select copy. And then in RS2, I will select paste from slide interpret. And you can see that the surface is very, very close. As well, the shear reduction factor, which is something like factor of safety, is 1.18. So that's almost identical to what we got in slide 2. The other thing I wanted to show you in slide is the impact of surface altering. So I'm going to click on my Cuckoo and I'm going to duplicate it. I'm going to call this one Cuckoo no surface altering. Then I'll go to surfaces, surface options, and I'll just uncheck this optimize box. And we'll compute that. So now it's only going to do the global search without the local optimizer at the end. So nothing shows up here. And then hit interpret. And we see that now the factor of safety is 1.26, whereas with surface altering, it was 1.19. So that's quite a significant difference in factor of safety. Okay, so back to the presentation. This is just a summary of the results we saw. So grid search was around 1.6. The non-circular ones were much smaller, 1.19, 1.15. The difference in surface altering, which we just talked about, you can see that there's very little difference in the surface, but it's been optimized to bring the factor of safety down. And over here, you can see it goes more in the weak orientation of this material. And finally, the shear strength reduction verification, which, as we saw, the surface is very similar and the factor of safety is also very similar. And now I will pass the presentation on to my colleague Terence, who will take you through multimodal optimization.
All right, thanks, Brigid, and thanks, Brent, also for the introduction. Hi, everyone. So I will now turn us over to discuss our newest search method, which is called multimodal optimization. And in fact, we already got a few questions about this, which makes this very useful. So the primary motivation for this method lies in the fact that a slope model can have multiple modes of failure, Just like in many other optimization problems, we are sometimes not only interested in just the global minimum, but we are also interested in the results of local minimums as well. The goal of multimodal optimization is to find multiple slip surfaces in a model, which correspond to different local minimums. In this way, more than one failure mode can be considered at the same time for a design. We will call this method MMO for short. And that's what I will be used to refer to this method for the rest of the presentation. So now MMO still uses a variation of this particle swarm optimization that Brigid mentioned. And there are actually many ways to alter the behavior of these particles in the ways that they move relative to each other. So previously we had particles each move towards their own personal best solution, as well as the global minimum solution. But now in MMO, we will instead have these particles move towards basically the two nearest neighboring particles to the individual best solution that the current particle has experienced before. So we look at the individual best, and then what are the two neighbors, and then we move towards those two neighbors. So the idea of this is to really just give a bigger search space during the search and not just have everything move towards the global minimum at once. And what it does is it seeks local minima instead of being pulled by the global. So we can do this in slide 2 and slide 3. I'll show the dialog for slide 2, but associated with, I guess, this new algorithm, we now have a few sort of new features that we want to highlight. So first of all, I do want to note that this number of failures multiple option is only available for particle swarm at the moment. And we have these 3 new sort of boxes here. The radius span of search space allows you to basically determine or decide how far apart you want the local minimums to be apart from each other. So for example, if you were to put a very low number here as a percentage, then you would get a lot of local minimums that are really close to each other in the model. Whereas if you have a really high number, then the results will be further apart. And then we can also cap the number of mins that we show in the results. So if this will sort of this will avoid sort of overwhelming the results with too many surfaces to look at. And then we also have this cap max factor of safety feature where anything above the value I put here for factor of safety we'll simply ignore for the subsequent surface altering stage and ignore them in the results as well. So up until now, everything we've discussed in this webinar has so far applied in slide 2, and we've shown a demonstration. Brigid has shown a demonstration of how all these features work in 2D. But now we will also address 3D searching in our slide 3 products. And I will have a demo to show for this as well. So in fact, as we've intended, there's very little difference between the searching methods in slide 2 and slide 3. And in this section, we will cover the small differences between these programs when it comes to searching and also provide a demonstration. Obviously, we're dealing with 3D slip surfaces instead of 2D, so it's going to be a little more complicated. Obviously, we can't draw a simple 2D polyline to basically define the surface anymore. But instead of these polylines, we now have to use these ellipsoids. And so what it is the particles are now being defined using ellipsoids rather than the polylines. And we use these ellipsoids to sort of transform them to get to basically search for the minimum surface. And obviously, when these ellipsoids intersect the ground, the intersection creates a slip surface that can be analyzed. So to be very clear, an ellipsoid can be defined using an origin point in XYZ, then also 3 radii in its principal axis directions, and then also we rotate the principal axes using 3 angles. And then just like in 2D, as I mentioned, the particles are defined by these ellipsoids and they move towards each other. using either the unimodal search, which was the very first sort of before we had MMO described. It'll just search for one minimum. So we'll call that the UMO for now, unimodal. And then of course, there's also the multimodal search option as well. And so just to show sort of an example here, we conducted a unimodal search for this pit. And we did it over the entire domain. And we found that at the far side of the slope, we had a factor safety 1.0. However, if we actually isolate the search region to be on the near side of the slope, then we actually get a very similar slope surface as well, of factor safety also around 1.1. And so you can see here that unimodal would not have been able to find the surface unless you had explicitly defined the search limit. Whereas actually we also ran this model in MMO, and in this case the program was actually able to find both failure modes. And so this is useful because you can find all of the critical surfaces in one computational without having to define any search limits. You could define two search limits in the model. So that was sort of the green box you saw back here. And that would work too. So it would compute both areas and give you the minimums for both. But then the issue with that is you might not actually know beforehand where the failure modes are. And so MMO is sort of a nice way to automatically identify them. And again, it's always a good idea to do some cross-program verification. So we use RS3, use our RS3 products. So Brigid, similarly with Brigid doing RS2 on her slide 2, we did RS3 on our slide 3. And we ran the shear strength reduction and we found very similar results. The critical slip surfaces were very similar and the shear strength reduction results were pretty much the same as well, with 1.0 and 1.1 shear reduction factors. So that's good, it matches, that kind of gives us more confidence in our results. And so I'll now go into, I guess, the last demo for the day. And this example here, you can actually access it in your tutorial files. So if you downloaded the newest slide 3 update, you would have had this new tutorial file that you can play with. And for this one, we will particularly look at the results of MMO and also assess the relative impact of the surface altering algorithm it's both available in slide 2 and slide 3. And then also at the end, we'll do also a 2D section comparison where we actually analyze the critical slip surfaces in slide 2. And there's a very easy way to export that and be able to do that automatically. So I'm just going to show us the model here. So here you can see we have a sort of a pit with two sides. There's this really steep face on the left, and also on the right there's a lot of things as well. The model actually has two fault lines. So these we've defined as weak layers. And what these weak layers do is pretty much unique to our program is if you were ever to draw like an ellipsoid or any kind of failure surface and it goes through one of these weak layers, the program will automatically check if the weak layer reduces the factor of safety by cutting the surface. And it'll do this for all of the weak layers in the model automatically. And so I just wanted to go over the slip surface dialog, the slip surface options. And so similar to slide 2, you have a few options in this dialog for how you want to make your search. We're going to do the ellipsoids here, as I mentioned in the presentation. You can also do spheres, which are a little bit more primitive. And then there's the multiplanar and wedge options as well, which we won't cover today, but are available in our tutorials. There's the weak layer handling sort of algorithm that I briefly mentioned just now. So this automatic case generation does exactly what I just described. It takes all the weak layers and checks if they can intersect the slip surfaces to create a lower factor of safety. But if you know that the highest weak layer in your model governs, then you can also just snap to the highest layer by default. That will save some time in your computation. And here we have the particle swarm search enabled. You can also use cuckoo search. And the benefit of particle swarm here is you can use the MMO algorithm. And if you open up the options, it has all the settings that are the same as slide 2. You have your radius span, cap number of minimums. So we're going to do 4 minimums here. And also anything above factor safety 3, I'm not going to consider. And then we'll also toggle the surface altering optimization on. And I'll actually show you the difference of the results between having this on and having it off. And so to save time, we pre-computed this model. And you can see the results. I mean, obviously, if you wanted to compute, you just click the compute button, and it takes about 5 minutes for this tutorial. And here you can see that the MMO algorithm has found 4 sort of local minimum surfaces here on both sides of the pit. And the nice thing about this is you could click on the table down here at the bottom right. You can click on these ones to sort of highlight which failure modes which correspond to which factors of safety. You can also use the drop down up here to do the same thing. You can show them all at once, which I did before. For this tutorial, we ran Bishop and Yanbu, so you could run those results as well and view them. I did want to showcase our show all surfaces dialog. So for this model, we actually had a search limit, and it sort of limited the search to within this region. And if you were to click on the show all surfaces button at the top, you'd be able to see all of the surfaces that were generated during the search. Just quickly load it up. And yeah, so here we can see that during the particle swarm search, so this is a list of all the surfaces generated during the particle swarm, with exception to the global min. The global min just shows up for everywhere because it's important. So you can see here that if we show only the selected outline, these particle swarm search was only able to find surfaces down to maybe 1.43 factor safety, and then with surface altering, we were able to get it down to, I believe for this one, 1.242. So this is the altered surface here that I've highlighted, and then the particle swarm ellipsoid that generated here was 1.44. And so you can see really clearly that there's a real benefit to using the surface altering algorithm. In fact, if you use softwares that don't have this feature, surface altering, then you'll often come up with sort of fictitiously high factors of safety. And so you really want to have a good local minimization algorithm as well when you're doing this sort of search. I did want to do one last thing here, was to show some of the 2D sections that we computed. So I've clicked on this slide 2 section creator, and I've created some sections beforehand. But essentially what it does is it gives you a preview of the results, and then you can draw your sections into the model, and basically what it'll do is it'll automatically analyze them in 2D. So just got to figure out why they've disappeared. Let's try this, refresh. I'm going to try refreshing the slide 2 results. There we go. So what I would have done is, obviously I've pre-computed this to save time, but I would have just clicked on this button up here, slide 2 compute, and it would have done the analysis of these sections here in slide 2. And it turns out that the factors of safety on the right side, I could have done it on the, I could have done the analysis on the left side as well, but the right side was a little bit more interesting to us. And so you can see that the factors of safety and also the critical slip surfaces here obtained from slide 2 are fairly similar. And as expected, the factor safety slide 2 is a little bit lower. But yeah, also it's worth mentioning that slide 2, when we exported these sections, it actually went and did a cuckoo search, and it found that these were the failure modes. So I think that's pretty much concludes the demo here. I'll just sort of summarize what we've gone through for this presentation. So in terms of the MMO results, we found failure modes on both sides of the pit with similar factors of safety. If you had just done the UMO result, you would have gotten one of them. And then we did the surface altering, and we showed that it actually reduced the surface factor of safety by 20%, which is quite significant. And then we had a 2D section analysis at the end, where I actually ran the left side here when I was doing it. So obviously the independent search that was done in 2D was able to find very similar failure modes, but it is worth mentioning that the 2D analysis might not always give you the same as the 3D, just because of the 3D geometry effects that aren't captured in slide 2. And then also for the same surface, the 2D results are usually slightly lower. Again, that's because of the geometry effects in 3D. And yeah, so basically that sort of concludes my section. I think at this point I'll just pass it back on to Brent to offer some concluding remarks.
Thanks, Terence. Thanks, Brigid. I'm just going to go over a few remarks that I have concerning searching and stability analysis in general, and some of the things that I've sort of noticed over time. Now, the first one is obvious from this webinar, that we're continuing to improve and provide some of the best searching algorithms there are out of any commercial product on the market. And one of the questions that we often get is, I've got a old version 6 of Slide, and I've upgraded to Maintenance Plus version 9, and my results have changed. And why? And the answer to that is quite simple, is that over time, we work to improve how we actually do our searching. So you should notice over time that there are improvements in how we do searching. And in particular, now that we're doing 3D, I expect over the next 5 years that you'll see big changes in how we're actually doing the searching, as because searching in 3D is a much more difficult endeavor. The second thing is that surface altering is really crucial, as we've seen. And one of the questions that I have personally, when I read a lot of journal articles and I read a lot of statements, is what should I expect between 2D and 3D factor of safety? And Terence pointed out something very interesting, that if I just use a simple ellipsoid and I do my searching based on an ellipsoid with one of our advanced metaheuristic algorithms, in his example, he gets a factor of safety of around 1.5. Now, if you apply surface altering and you do the same analysis and you take the ellipsoid and alter it, you end up with a factor of safety of 1.3. So that's about a 20% drop. 2D, from what we've seen with cuckoo search and surface altering, is about 1.1. So it really depends a lot on how you do your searching, what that difference is between 2D and 3D, and how you do the searching in 2D and how you do the searching in 3D. And the numbers indicate that in Terence's particular problem, and it does vary problem to problem, that he's seeing a difference of around 10 to 15% between 2D and 3D. Now, I'm sure a lot of you have sort of heard numbers like 30%. And, 30% in some problems is accurate, but I question that, this 30%, which is what we saw between 2D and ellipsoidal searching, is the 30% really a function of 3D, just the 3D nature of the problem? Or is this 30% an indication that we're not searching correctly for the global minimum factor of safety surface? And what I've seen over the last 3 years is that I don't think we're searching as well as we need to in 3D in order to achieve the true global minimum factors of safety. And as Terence showed, we have run numerous 3D RS3 analyses on these, and that they seem to indicate this. So I think this is something that over time, will become more and more apparent as to, what is that true difference between 2D and 3D. Okay, another interesting question is it okay to start with circular searching, grid searches, auto-refine? And what about non-circular? And it was interesting from the actual poll that over 50% of people say they're doing circular searching. And circular searching is fine. And certainly it's easy to do, and you can start with it and sort of get an idea of what your factor of safety is. But my recommendation is please don't stop there if you start with circular. That please use some of these advanced non-circular methods. As Brigid highlighted, certain types of modeling on certain types of materials, such as anisotropic materials, right, display a uniquely non-circular surface, failure surface. Plus, I also see that people are using circular searching on a lot of friction-only materials, cohesionless materials. And, theoretically, in a frictional material, your failure surface is planar. So why would you use a circular surface when dealing with those types of materials? Now there are cases that you want to do circular searching, and one of those cases is if you have a undrained material, a frictionless or cohesive material, CU. And in those cases, circular searches work quite well. So I think it really depends a lot on the problem you're trying to solve, but be wary of, how you're doing your searching and what kind of materials you have. And please do not stop with circular. And please use some of these more advanced methods for hunting for the global minimum using these optimization methods and surface altering and all the work that we've done over the last 15 years or so. Okay. My next is use multiple search methods. One of the questions that we always get is that, I use this method, I'm getting a different factor of safety than this method. And my answer is, there are a lot of searching methods in slide. And believe me, if there was one method that always worked for all possible situations, we would only have one method. But that is not the case. That really there are cases, and we are improving over time, but there are cases which are better handled by different search methods. And I would recommend that you do try some of these different search methods like cuckoo search or particle swarm or multimodal particle swarm or simulated annealing, or even things like block searches with optimization if you have some idea of where the surface should be. And that leads into my next comment, is that always use your engineering judgment, right? And you should look and see, is what my program, and it's just not Slide, it's any other commercial product out there, is the surface reasonable and what you might anticipate? look at the normal stresses on the base of the surface. Do they make sense? Is there a lot of tension on the base? And tension, as we know, has a very adverse effect, especially in materials that can't take tension, like a lot of soils and a lot of rocks. If they can't take tension and you allow tension to occur on the base, the tension can have a very adverse effect on the factor of safety. If that tension is near the toe, it can give you a fictitiously low factor of safety. If it's near the crest, it can give you a fictitiously high factor of safety. So, you know, a lot of people understand that we should be using tension cracks and things like that, but, you know, make sure that you look at the stresses on the base. Check your input. I can't tell you how many times I did technical support and somebody sent a model and said I added water, but the factors of safety are the same. And you look and you see, okay, well, the water wasn't properly applied to a particular material. And if you look at the pore pressure on the actual failure surface, you'll quickly see that it's 0. And then obviously you didn't properly apply it and you can go back. So basically look at some of these parameters that you've defined, right? Look at the material strengths along the failure surface, okay? Use our safety maps. We didn't cover a lot of that in this webinar, but in 2D, we have great safety map technology, which gives you an idea, what the spatial distribution is, a factor of safety. And in 3D, we have the same facilities, but on the surface, you can sort of see where the low factors of safety are. And these methods are actually improved with the use of multi-modal optimization. Okay, and SSR is very useful for validation. Okay, we saw with Brigid's example that it is really easy to use our RS2 product with Slide. We designed it to be really easy to use. RS2 has every material model that is in Slide. So, you know, a lot of other finite element programs out there do not have these models. So if you've got a Slide model, RS2 is the better vehicle to actually do your SSR analysis. It's easy. You drag and drop. It does everything for you. You hit compute. It is, and it only takes maybe 5 or 10 minutes in most cases to run the analysis. So it's just a secondary method for you to validate that you're getting the right factor of safety. And then finally, over the last 5 years or so, we've worked extensively with a number of industrial partners like IDS and Ground Probe in order to take into our 3D packages like Slide 3 and RS3 radar and laser scanning displacement data. And this radar and laser scanning displacement data can be shown with the actual factor of safety surfaces. And this can allow you to easily back analyze what your properties are, where the location of the global minimum is, and the size of the failure. So now we're getting into that realm where we can take data from field measurement, such as LiDAR, radar, and actually incorporate it into our analysis to make sure that our results are accurate. And that sort of completes the webinar. And I'm going to turn it back to Terence for some news on our upcoming conference.
Yeah, thanks, Brent. Before I go into that, there will be a time at the end for us to answer a few questions. We know that it'll run a little bit over time, so I do believe we are sending out some generic responses to sort of a catch-all for all the questions that have been answered. So stay tuned for that. But we did receive a lot of questions, so we'll try to sort of bunch them together. Just a reminder to sign up for our upcoming conference. The conference is held from April 20 to 21st, and keynote speakers include the very well-renowned Dr. Everett Hook, Dr. Bodden, Dr. Foon, and Dr. Seaton, all very well-renowned in their fields. We have panel sessions as well on numerical modeling and its integration with monitoring instrumentation. The panelists include a suite of industry godfathers. It will be a great event. Registration is again through our websites. And then we also have a finite element workshop coming up that will be run in the days just before the conference. And the course will be led by Dr. Reginald Hama and Dr. Alireza Azami.